Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at solving modulus problems to do with graph transformations and modulus functions, etc, etc. So wrapping up all that we've done in chapter 2 all into one section and combining it into one question. So let's have a look at a question then. So a function t of x, okay, we haven't seen t used many times for functions, is 3 modulus x minus 1 close brackets minus 2. X exists in R. So sketch a graph of the function, state the range, and solve the equation that t of x equals a half x plus 3. Okay, what I'm going to do then is I'm going to build this graph up in stages. I'm going to start with the y equals modulus x transformation and then apply 3 transformations onto that modulus x standard graph. Start with modulus x. And we've got a couple of choices to start with first. We can either move right by 1 first, because that's inside the brackets, and then we've got 2 that are happening outside the brackets, and it's important that we do those in the correct order. We would have to apply this one first and this one second, following the rules of BODMAS. So, let's move it right by 1 first. And just trace your coordinates as well, because that's going to really help us in part B later on. Now let's stretch upwards and downwards by a scale factor 3. So I would draw out all of these graphs if it were me doing an exam, okay? It's not just me showing you how to do it. I would actually do it this way if I were doing a question like this in a class or in an exam. The last transformation we need to do is move it down by 2. So the minus, it'll be at 1, negative 2 as the minimum coordinate and 1 on this y-axis intersection. And I would probably draw the final graph here just a little bit bigger so that I know that I'm going to have to draw this graph on top of it so that I've got enough space to do that. State the range of the function. Now the range of the function is just all the possible set of y coordinates. And it looks like this is greater than or equal to minus 2. So greater than or equal to minus 2. Make sure you put t of x is greater than or equal to minus 2, or y is greater than or equal to minus 2. Now let's go ahead and solve the equation of a half x plus 3. So let's draw this graph onto the sketch that we have here. So it's going to intersect at 3, and it's going to have a gradient of a half. What does the gradient of the red line have? Well, if you can imagine just kind of expanding the brackets, this would have a 3x gradient. So when you're drawing these types of graphs here, do consider what gradients you have for your question, and the steeper gradient must visibly be steeper than the other gradient that should be shallower. And what we get here now are 2 solutions. We get an A solution and a B solution to these intersections. For the B solution, the slightly easier one first, finding the first solution on the non-reflected part of the graph. Remember, this is the normal part of the graph. This here is the reflected part of the graph of modulus x. We're just going to solve this normally, so this is the B solution. We set a half x plus 3 equal to the equation of the graph. This is not being reflected, so we can just get rid of the modulus brackets and put a normal pair of brackets there instead. So that's on the non-reflected part of the graph. Okay, let's go ahead and now solve this. And we get x is equal to 3.2. So our B solution here is at 3.2. The next solution here is going to be found by the reflected part of the graph. Now on the reflected part of the graph, this is actually a negative gradient. So inside here, we need to have a negative symbol in front of the 3x minus 1. Effectively, there now needs to be a negative symbol where the modulus x minus 1 brackets appear. So this solution here just got a normal pair of brackets. Normal brackets. This solution here, because it's on the reflected part of the graph, gets a negative pair of brackets. So it's really important that these are the distinctions between this solution here and then this solution here. on the normal part of the graph that's not been reflected, it's just a normal pair of brackets that replaces the modulus symbols. And on this part of the graph here, where it is the reflected part of the graph, this is actually a negative gradient, so we need to put a negative symbol in front of the brackets where we get them here. And it's just easier for me to write this negative symbol in front of the 3 rather than just in front of the brackets. So let's now go ahead and expand these brackets. And we get x equals minus 4 over 7. Okay, so our two solutions are x equals 3.2 and x equals minus 4 over 7. So once again, one of these solutions just needed the modulus symbols to be replaced by a normal pair of brackets. For the other solution, on the reflected part of the graph, the modulus brackets were replaced by a negative pair of brackets. Okay, final question then. So f of x in this case here is 6 minus 2 brackets x plus 3, and we're given the graph this time. State the range of f of x, explain why f inverse does not exist, and solve the inequality for x is greater than or equal to 5, greater than 5. Now, for the range part, since the modulus part is positive, we are going to be taking away a value which is greater than or equal to 0. So the largest part of this graph is 6. So because this modulus bracket here will always give me a positive or 0 solution, 6 minus this thing here is going to give us a max value of 6. So in this case here, the range is going to be y is less than or equal to 6. Okay. Explain why f inverse does not exist. Well, if you remember that inverses only exist for one-to-one functions. This here is a many-to-one function. So the inverse does not exist here. The function is many-to-one, as different inputs can give the same output. The inverse would be one-to-many, which is not a function. Okay, so this is not a one-to-one function. Only one-to-one functions have inverses. Now we need to solve the inequality of f of x is greater than 5. And it looks like it's just for a very small part of the graph in between here and here. So what would be a good idea to do is to solve the equations of this function here equals 5, and there are our two boundaries. Now for the non-reflected part of the graph, that's this part here, we're just going to replace the modulus brackets with a normal pair of brackets. And solve this equation. We get x equals minus 2.5. So that's this solution here. Now for the reflected part of the graph, that's this part here and this solution here, we're going to need to have the modulus brackets replaced by a negative modulus pair of brackets. So in this case here, it was a negative and now it's turned into a positive. So effectively we've had a double negative happen there. Rearrange this equation, and we get x equals minus 3.5. So minus 3.5 is our solution here. So what's the answer to this question then? Well, we're looking for when the graph is bigger than 5, so it's just inside this region here. So x is going to be in between minus 2.5 to minus 3.5. Okay, your turn to have a go at this question here then. So have a go. Part B is a little bit tricky. We haven't seen a question like this, but I do want you to give it a go and see how you get on. Use the graphs to help you in this question. Right, okay then, let's have a go at question A then. So drawing the graph, what I'm going to do in this case here is I'm going to use 3 different graph transformations starting from the original modulus x graph. The first transformation I'm going to do is I'm going to move right by 1. So in this case here, I'm going to move it right by 1 and I'm going to track some coordinates. 1 and 1 are going to be the coordinates there. The next thing I'm going to do is I'm going to times by a scale factor of 2/3 onto all of the y-axis coordinates, because this transformation here is outside the brackets affecting the y-coordinates. So the one coordinate on the x-axis is not going to change, but the one on the y-axis is going to get transformed to 2/3, so it's just going to be a little less steep. The next thing I'm going to do is I'm going to move down by 7, because there is a -7 at the end of the transformation. So in this case here, this 1 coordinate here will move down to the coordinate 1 minus 7. The 2/3 is going to move down to -6 1/3, and then we can draw in our graph around this. Okay, so that's what the graph there is going to look like. Part B is to now state the range of values for which k equals 2/3 x plus k has no solution. So let me just grab a different coloured pen to have a go at this question with. So 2/3 x plus k. Now in this case here the gradients are going to be exactly equal, so I want the equation of my line to be exactly the same gradient as the lines I've already drawn on my graph. Now really what I would quite like is for it to have no solutions. It cannot intersect the graph at any point. It looks like the first time that can happen is if it just slightly goes past this coordinate here. So really what we'd like to know is the value for k. Now what is k? K is going to be the y-axis intercept. So what's the value k here, such that if we were to go up and intersect this 1 minus 7 coordinate, and then we want it just a little bit less than that. Okay, so carrying on, so what we're looking for now is for the intersection of y equals 2/3 x plus k with 1 minus 7. We're looking for when this intersects it exactly, and then we can just have k be a tiny bit less than that, and then that's a fine value for k. So substituting these values in, we get -7 equals 2/3 times 1 plus k. So in this case here it's going to be -7 2/3, which is equal to k. Let's turn this into a top-heavy fraction, so that would be -21 minus 23 over 3. Okay, now -23 over 3 will give us an exact coordinate that will intersect the 1, 7 coordinate at. So in fact we want k to be less than -23 over 3. And that's the answer to this question. State the range of values for k for which the equation has no solutions. This is our answer. Okay. So then, we finished chapter 2, finally. So, have a go at lots of questions from exercise 2G, and have a go at some of the mixed exercise questions as well. There is a lot in this chapter, so well done for persevering through it. Make sure you have a summary by doing some of the mixed exercise after having a go at exercise 2G. Okay, great. Thanks very much for watching.